So, hi all, welcome from Madrid. We today have another intense section with a couple of very interesting guest lectures. Now I will show you the agenda of the day. So essentially we will have a first, after this introduction of the agenda, we will have a first lecture from me, which is more or less following the main thread, which is inspired by Rolf's book, How the Body Shapes the Way We Think. So where we actually push our idea of the general idea of embodying intelligence. And then, today's topic will be design principle of intelligent systems, implicitly according to an embodied intelligent point of view. Then we will have a couple of uber cool lectures. One from Kevin O'Regan about the possibility to how to implement a sense of self or feeling into robots, into artificial systems, generally speaking. And another one on the topic of soft robotic manipulation. So how you can develop an arm which is not as rigid as conventional, as current technology shop floor welding arms. So you will notice a certain leap from one to the other, but actually one of the points that we stress is that we need a broad spectrum of competencies to approach intelligent system, natural intelligent system understanding and artificial intelligent system development and design. So, and finally, after that, I will do a few remarks on the issue of the brain in the vat. No? So, because we actually launched the challenge to the students, and we had a presentation from Xi'an a couple of weeks ago, and so it would be nice to have actually a few minutes of discussion of this after today's lectures. So just to where we are, no? So we design principle. So this is lecture number 7, and now I give a very short presentation of the 2 guest lecturers of today. The first one is Kevin O'Regan, that you can see is the white-haired person in one of the screens. Actually, he did many things. He was the former director of the Laboratoire de Psychologie de la Perception at the National Research Council in Paris, at the University Paris-Descartes. Actually, he achieved several insights about the topics that we are discussing, because actually in his PhD he was able to show the existence of an optimal position when the eye fixate words. Then actually I think one of the great contribution was, from my standpoint, was that by questioning some established idea, and we will go in detail on this, more in detail on this later. Actually, he was able to predict the phenomenon of change blindness. No? So I'm sure he will show some experiments of the fact that sometimes we really don't notice big changes in scenes that we are looking at. Actually, now is actually working on a sensory motor approach to vision and sensation in general. And it is worth notice that he published recently, so he did many things, so I'm sorry if I shorten a bit, but actually he recently wrote a very interesting book which was published by Oxford University Press, which is as an intriguing title, which is Why Red Doesn't Sound Like a Ball. No, which is, you will understand what it means in about 40 minutes. Then the other talk will be from Shen Wang, which is actually from Shanghai Yaotong University, and is actually working from a more engineering-oriented robotics standpoint, and of course he's an author of many research papers, and is an editor of RAS conference editorial board, and actually is, we don't see it, but he is the program chair of Robio, Robotics and Biology. Robio, one of the leading conferences in robotics oriented to bio-inspiration in 2014. So, and that's all. So, all as regard the agenda. Now, and now we enter into the into today's topics. So, as I told, design principles for intelligent systems. In which sense? From the point of view of embodied intelligence. So what we have learned so far. We do a small recap, and then we will go into this concept where mainly we will force the idea that the intelligence is actually a characteristic of a complete agent, not just a logical function that you add on from the exterior at some point. And then we will exploit, see other approach. So what, just to do a recap about, because what we have learned, or at least stated so far. So what we are actually challenging is the traditional idea of cognition as computation. You may remember what we told in the previous lecture. So it's really hard to agree on a definition of intelligence. No, we have had some fun about the IQ or maybe other metrics of maturity, intellectual maturity, based on some algorithmic measure. And we have seen that from the very beginning, probably a valuable approach to try to understand if a system is intelligent or not, it has to be empirical. No? So the first seminal example is the Turing test, where actually we do a kind of competition between the system and the human, and we check if the interrogator is able to distinguish. If it is not able to distinguish, we assume that the system is intelligent. And this, which is a purely empirical approach, which tries to stay away from giving some definition, because we have problems to really capture what really intelligence is, where it is prone to, as we saw, to a serious argument, which is the Chinese room Foyt experiment. Now, where Searle, who didn't speak any Chinese, said, well, put me in a room with a long enough list of rules, and I will be able to give proper answers to the question that you ask me in Chinese. This is a way to say that maybe, in principle, the system could pass the Turing test without really understanding anything of what it's doing. I think this could be questioned, but for instance, I don't know how long this rule set should be, and how physically the information and the energy used in the Chinese room would affect the final result. So, because actually we continue to use logical abstraction, but even what we call the standard symbolic processing on standard computer is a physical process, where maybe the physical process is not as important as in human locomotion or animal locomotion, but as its impact. So we introduced the concept of Turing machine as a universal calculator, and actually also we showed this now, so that with a Turing machine, the big problems could be to match, it's clearly to match one of the assumptions that is to have an infinitely long memory, right? Memory strip. And this is a cartoon by not significant from a physicist, which is always Roger Penrose. So, as a summary, because this is what we are trying to cope with. So we would like to go beyond the limit of what we dub as the classical approach, which is an approach which is still used for many applications and for many useful research and valuable researches. So the classical approach is actually can actually spot some important successes from search. On the web, Google is probably is the biggest and more visible success of artificial intelligence the old way. About is an old way strongly affected by stochastic and statistical methods. So it's not, it's I would say the most open-ended approach to classical AI that you can think of. Chess. We know that the world champion is actually of chess is actually a computer program. And manufacturing. We know that today, for instance, all the cars that we see around have been partially manufactured by robots. We also know, and this is what we are trying to stress, and this is what we try to cope, because actually the aim of this embodied intelligent approach in both AI and robotics is to go beyond this kind of limitation and to develop systems which are actually able to interact in the real world and with humans. We also see some failures that you can see on the other sides. After 50 or more years of research, we know that this current approach is not able, or was not able, but probably is not able to cope with some apparently easy tasks, easy for us. So, for instance, it was not able to find a realistic foundation of behavior, was not able to develop, as not being able to develop a kind of what we dub as a natural form of intelligence, which means that if I look to the chessboard, I can think to play chess according to the chess game rules, but I can also use to play dart with it and to invent a strategy to play dart with the chess board. This is completely unmet, or very largely unmet by existing systems. And then the interaction of real world is really usually poor. So there are many systems, but including you have seen, for instance, in the presentation by Professor Krajic, some very nice approaches to manipulation and also grasping in a semi-structured environment, which is your house, a model of house. And this is already very difficult with current systems. So there are significant failures. And if you think about it, sorry for repeating, but this is typical of teaching, right? We really have a kind of significant difference. This was also shown by the comparison by Asimov falling from the stairs and a small, simple process into a cell. Robots are based on a conceptual approach, which is, if you want, Cartesian, mechanistic, deterministic most of the times, and the better success are when you include some machine learning procedure into the loop. While humans are like a living system, have a completely different approach. They don't care a lot about precisions. precision, they are compliant, reactive, and they cope with uncertainty. So it seems that we really have a difference in paradigm. So, and what we try to define with design principle, what we are kind of to present today, is actually to find, to find a way to develop artificial systems that on one side would shed some light on the of a natural system. We discussed it also about the synthetic methodology approach. On the other side, would be we hope are able to do things that current artificial intelligence and robotic systems cannot do. So we just to finish and then to, and this I think we think should be seen more as a research program. So this is not complete. We are not discussing about a new robotics technology which is well formed and already we can show in the streets the robot inspired by that. We are talking about a research program. If we are lucky for the next decade, if we are not lucky, or if we have not enough funding for the next decades, no, but really we are looking for a way to get beyond the limitation of the core approach, and which, in short, now this could be a could be a series of lectures in itself, which are the main issues of the classical approach. Letting alone the homunculus problem, which is the tendency to say, to solve the problem, to say, but in the brain there is another system which does that. At least we have two big problems. One is the symbol grounding problem. So, unfortunately, in the real world, we don't have the names of the things painted on them. And it is interesting to notice that something that you do in some application is to use RFID tag, which is a very simple way to put a name on an object, right? And the frame problem, actually, I don't want to retake all the discussion, but it's something that we still really we should never forget, is that if we want to design a standard, block-based or any language, kind of language, Lisp or C, whatever language you use, the tiled model of a word, you will have to add details. Now, the DNet example that we was discussed by Rolf a few weeks ago is actually you never finish to add details, and the real problem of artificial system is that it's not able to do a difference between what is relevant and what it is not relevant. So, and this has an obvious consequence on the number of steps of computation that your system will do. No? So, to make a long story short, and sending you back to what we said before, actually we are distinguishing two views of intelligence. One, which is prone to, for instance, to the symbol grounding issue, and the frame of reference. Mainly, the frame of reference issue is the classical approach of cognition as computation, and the other is what we are looking for, which is the idea of a cognition which emerges from sensory motor and interaction process. So the main point that we raise, and I'm not going through all this discussion again, is that really the fact that the interaction is mediated by the body is the real is extremely important into into the natural intelligence. So just to stress again the frame of reference issue. So what we now the Simon Sand on the beach. So what's the relevant about this picture? What is relevant is that this hand, which will move from the nest to the food, actually seems to do very complicated things. But actually, the most of the complication in the trajectory comes from the environment. So he has simple rules to adapt to to pursue its objective into the environment, and this results into what an external observer could see as a complex behavior. And this is another issue, because the typical approach to computing or to computer programming is that we develop so we are in some way we inject our knowledge of environment into the system, while and this is what makes the system weak with respect to small changes in the environment. The symbols and the representation of the environment should emerge from the system according to the interaction of the system, and the system should be able to create something new in front of something new in the environment. And this is something that most of the time we are not able to put into an artificial system, and what we should try to do. Right? So just make this to understand the importance of the environment. So usually the natural intelligence systems that we know are in open-ended environment, but in well-identifiable environment. So if you think, for instance, to this ant, think for a while to this. What if I increase the dimensions of the ant by 10,000, leaving the beach as it is? It would not work anymore. No? So this is what we will put again as the ecological balance. No? And so we have a number of issues which came out of this frame of reference issue. So the perspective, and then so it's actually, but the main limitation is that I know what is in the environment, which means I, human, represent the environment according to what I know of the environment, and I carve it into a computer program. And this seems implicitly means that if I don't know everything about the environment, I won't be able to really develop a system able to cope with it. And then there are how and we can think to design a system to get rid of this kind of limitation. The first observation is that we should look for a design approach which doesn't look at a specific, doesn't look at the beginning at the specific characteristic, but look at the design of a complete agent. So, for instance, taking from this cartoon, so you will have to design a system which is actually able to self-sustain. This fungus eaters is fictional robots which use it for space exploration and to find uranium on outer planets. And it eats fungus and it has it will have some sensing. For instance, if it is looking for uranium, it will need a Geiger sensor or things like that. So which are the properties that these embodied agents should have? First, they need to be subjected to the law of physics. So we cannot even think of a system which is living some hyperuranium world. So the system that we know, the natural system that we know, which are actually outperforming the artificial system so far, are physical, and they are subject to law of physics. And luckily, we are looking for our scale application, and so it could be controversial, but we should think that macroscopical physics should be enough. And then the sensory stimulation should be generated by interaction with the world, the real world. Our system should be able to modify the world, because actually part of our understanding of the world is due to the facts. No? So if I don't see very well what this is, I move it, right? So think that a system which affects, for instance, a vision system that I saw recently. So if you put something in this way in front of a camera, it may have problem to recognize it if background is more or less silver too. But if no, sorry, I don't know if you see it. Okay, I'm trying to look for it. So you look, I am interacting with a physical world, no? And so if I want you to know, to see better what I'm doing, I have to move it. And this is also what I do if I don't see it. So maybe in artificial system you do it in a very basic way, because still we have serious technological limitations. But the concept that you have to move things to better understand them, it's also acquired. So also we have seen it in the manipulation system, vision system discussed by Danitza a couple of weeks ago. Then we are talking about, we have to put into the picture complex dynamical systems, and we also have to consider the fact that our system, this is actually what we will go more in detail, I think today and maybe also next week, is this concept of morphological computation, which is the fact that when I work, now I don't know, I don't want to create too many problems, but when a person works, which works in a very different way from a robot, actually is a controller fall, and I don't do as much calculation as a full controller that way the system will do. And this can be interpreted as by saying that part of the calculation is actually performed by the system. And so now I don't know if someone in the when I say complex dynamical system, I also stress a concept that usually in engineering system it's a good approach for many things, including control of train brakes or things like that. We refer to a linear model, while in these complex dynamical systems, embodied system, the non-linearity play an important role. So I guess, does anyone in the global lecture hall want to give a short description of the difference between a non-linear system properties? So which properties differentiate a non-linear system from a linear system? So which are the differences? So someone want to try? Someone want to try? It seems that we don't have many volunteers. I mean, just about what I want to say about giving answer or raising question is that in principle they are not wrong. Well, they are more appropriate or less appropriate answer, but they are not stupid answer and not stupid question, because this question actually situated. No? So it depends on what you are thinking about. It depends on your background. So usually you may think that it is simple, something which is extremely difficult to grasp for most people, and to not grasping something very simple. So this is highly subjective. So the main difference, I would not like to give the answer, but the main difference between a linear and non-linear system is that in linear system you have small input changes lead to small output changes, and and you also have superposition of effects. So if you choose small effects, you will have the output will be more or less the sum of the outputs of the first input and the second input. This doesn't happen with non-linear system, as I think you know, but you don't dare to say. Many of you know, but don't dare to say in public. Is that in a linear system you have a typically you have a butterfly effect. So you can have a very small change in the input which give rise to a huge difference in the output. Or on the other side, you can have a very big changes in an input signal and almost no output on the other side. And this capability is heavily used in natural intelligent system. And if you think about any to the robot that we have seen, from Asimov to the Holding Arms to some others, they are mechanical system, and mechanical system are by definition not linear because they have a trigonometric function linking a joint to another one. So the reason why many robots are so big and heavy is that they have a lot of inertia to try to have a behavior which is as linear as possible. So one of the benefits of exploiting, for instance, non-linearity in the design is that you could afford much lighter structure for doing the same task, so to keep the same payload. And if you think about it, this arm is really light with respect to the arms that you see typical in a factory, which are in the 100 of kilograms. So this emphasis on non-linearity, softness, has an impact on the possibility of building very cheap and very light structure on one side. On the other side, the fact that we understand that a lot of computation necessary, for instance, for locomotion. We see now in a minute I will show some example. Is actually a way to keep very low the low computing load on the brain, on the computer controlling the system. So this is interesting, as I told, because it shed lights on natural system and how they work. For instance, it seems unlikely that you can study the brain disembodied without considering that this brain is always in some physical system. And on the other side, as a potential disruptive application, really on the application side. So we are not, we are academics, but this is not an academic question. So if this approach is correct, we have a huge untapped potential also from the industrial and economical standpoint. So dynamical system, and we have to put into the story a number of strange and attractive area of physics, like dynamical system, complex system theory, I told about nonlinear dynamics, chaos theory. Stochasticity is a basic point, because the intelligent agent never knows what really out, as we don't know what's behind that door. So I don't know if there is an alien behind the door in front of me. Probably not, but I don't really know for certain, right? So the face modeling and the fact that nonlinear systems, which are subjected to chaos, actually have a limited predictability. So I don't need even to be an environment to have unpredictability. If I have a proper model of a system, it is already by itself, without interacting with anything, not predictable. And then this issue of the trajectory. The trajectory doesn't depend only on the control, the agent actions. It also depends on the environment. For example, the Simon's paint on the beach. And now, here we come with a list of principles. We list 8. Maybe they could be reduced to 2 or 3. but at least from the understanding standpoint, these are all characteristics. Now, because you know that in the very first lecture I ended by showing two things. I showed again Asimov, which I'm using as the kind of bad example, but it's actually it's important because it's a very good implementation of a paradigm and shows some limitations, and the SAL, right? So we are trying to develop criteria which allows us to build systems which are more like to the SAL. And today I think I will just show or give an overview and at least a couple of examples, and we will go more deeper into it next time. No? So one was already quoted. The fact that we should talk about a complete agent. So the agent, the physical agent in the world. The other point which is apparent in the cell is that we have a long, but also up in our brain, is we have a lot of parallel loosely coupled processes. The other one is that the symbol grounding and information or anchoring, whatever you prefer to use as a word, is something which should emerge from sensory motor interaction with external world. And then chip design, redundancy, chip design meaning that we should always, already from the beginning, design the system in such a way that we exploit the characteristic of environment. So don't build a very complicated ant if the task is to move from the nest to the food source and back. Redundancy, this is needed so having different physical processes, exploiting different physical methods, physical ways, pathways to do the same thing. The idea of ecological balance, so the ant will work if it is small enough to move on the and then to have more, and this is more, to have a value-oriented behavior. So the system should be able to do what, to have some generic rule to decide what to do, but cannot really be told exactly what to do, because we don't know where the system will be happen to. And so this just to this principle number one, which is three-constituent principle, is the principle of ecological niche desired behavior. So we need to think at the same time to three things. So where the system is going to act, which are the desired behaviors and tasks that we want it to perform, and of course how we design it. So there are examples. Now, for instance, in manipulation here, now the fact that a system is example what I was doing before. Now, by manipulation by object, you can make easier the perception. This is a work by Mehta and Fitzpatrick, but for instance, also Professor Krajic showed this similar application in her lecture. Just to finish, because I'm afraid I'm using most of my time. I already used most of my time. I want to finish with a couple of videos that we will discuss next time. So an important aspect is that we were emphasizing, which seems at first glance is one of the first things that you notice when you compare a living system to is the fact that there is these parallel loosely coupled processes working in subsumption architecture. So we told that this should emerge from the system-environment interaction, and this actually refers to a proposal by Brooks, and we will discuss next time. But okay, we will say, because Baxter is not well, it's partially inspired by this view, but not completely. This could be an object. But the idea is that we have a traditional classical cognitivistic approach, which was what we were blaming until now, which is based on the idea of so you can pose it is perception, modeling, planning, acting, or sense, model, plan, act, or sense, think, act, or percept, model, act. So, but the idea is that you have well separated modules performing, connecting the sensing to the actuator. And then you can have a behavior-based subsumption architecture where you have a number of parallel processes going together at the same time. Of course, the first method is probably easier to implement because you have the full control of everything. You can build your blocks, but this probably is less effective. So it could not be a case that in nature everything works in another way. Could be so. There are contingency, but it's when everybody do the same thing to solve the same problem, whether it is nature or humans, you have to think about why they do that. So example is, this is an old one, which is the robot Genghis, where here we have a lot of, but on this we will come back, the insect walking. So actually Olk Cruz, who is a German biologist, has shown that in the working of small insects like ants, you don't need a very sophisticated central control system. So the first idea that classical thinking people would think about would be to build a big computer, sensing, elaboration of sensing, a plan generator, a plan connected to actuators doing things. Nothing like that. A simple neural network connecting two closer legs. And who is doing the job? The flexibility of the legs and the environment. Now we may show an application which is, because this is interesting, but if I'm not now is very popular, because if you want to put a robot in your house, you need to have a working human-robot interaction. So let's an interesting example and is this Kismet, which is a system built on the basis of this approach. We are talking, as I told, the ideas that we are discussing in this lecture have to be seen as a research program. So we have prototypes. We don't have still, but look at this next video and tell me if it doesn't seem somehow natural.
Do you laugh at all? I laugh a lot. Carol says I laugh a lot. I try not to laugh at her. Okay. You're adorable. Who are you? What are you? Dude, I want to show you something. This is a watch that my...
So, while we look at the movie...
Yeah, look, it's got a little blue light in it, too. Like, I almost lost it this week.
Huh?
You know what it's like to lose something?
It looks, it looks very natural. Of course, it has a limitation. But as I told, this kind of implementation show that this could be the right way to go. We will discuss later in later lectures what we should do also to go forward. But I think many people think that this is the approach to go. And so I skip a bit about this issue. So you can actually, you have available all last year's lecture. This year we have really compressed the main thread of the lectures into a few slots. But on the website you have plenty of lectures on these same topics. For instance, what I'm trying to compress in 2 lectures. was in the past was also expanding to 4. And so an interesting issue that you can see about this kind of approaches, but does it scale? So it's okay for turning to the loud source, to the sound source, but it's also okay to emerge some kind of symbolic-like processing like we do. Is it enough? Or like the chimpanzee do? Is it enough? So this was the discussion that around in the 90s was in between Brooks and David Kirsch. It was interesting. You're not necessarily to say on which side I stay, but I think Kirsch has very good arguments, which is how we can scale. And then I just finish. We will next lecture will be more focused on locomotion and cognition, how cognition emerges from locomotion. And just to introduce the next lecture of the main thread, I show the video of Puppy on the treadmill, and then I finish. And maybe we can also see the same thing in slow motion. So what you see here is that what is relevant here, and here I finish, is that this puppy prototype, which is a kind of quadruped dog, is working without any sensor and without any control. We should think about it, and we will detail more what does it implies. Does it imply in the next lecture? Just to finish, because it's almost time. Well, it's we may still probably have a few minutes of break just afterwards. Just there is a connection to what Kevin is going to say later on, because actually he will focus on how this kind of a kind of perception can emerge from a system from the sensory motor interaction. And also this is a work where many results have already been obtained, among others, like the people who is here connected. But of course there is a long way to do. So think of this idea as a research program. So, and that's all for today from my side. I don't know if there are questions, but maybe we should leave a question to the end of a section. So since we are very late, and actually Kevin already commented on the brain on the vat, maybe we can come back on this brain on the vat, because I think that the brain on the vat example is really very typical to characterize what we are trying to say. So because the brain on the vat idea, as actually was pointed out before, is more or less that you can have intelligence or even consciousness without having any real interaction with exteriors. And I think that should emerge from something that we have said today and what we had said before, that really it's difficult to imagine to imagine a real system completely disconnected and only governed by a computer. I mean, I want to show any slides, but the idea is that, okay, probably you can build a matrix, but this matrix should be comparable in complexity and in subordinateness, to use Kevin's words, to the real world. So it's another example of maybe he'll pose the question. So, of course, I can imagine of a brain which simulate, which is connected to a computer which simulates a sensory stimulation coming from the real world and react to the actuation as the real world. But probably the complexity of this computer should be not so far from that of the real world. So it's a kind of tricky question. So because you could say no, it's not possible, or you can say yes, if your computing system is the universe and the connection are as complicated enough as complicated as the real connection that the body has to the exterior, but it's like saying that it's not possible. No? But it's not a real brain in a vat. It's a brain in a universe, in a different universe, connected in a very strange way. Maybe I don't know if. But we can come back on this. I don't know if Kevin wants to elaborate or.
Yes, so actually, there is a point which is a lot of people invoke the notion of complexity to kind of explain emergent behavior like consciousness, and I think that again that's a mistake, or rather, it leads to confusion, because I think it leads you to the belief that there's something magic that's happening suddenly, like a kind of phase transition. You think that, if you get some system that's sufficiently complex, then suddenly it will show a change in its behavior and it will become conscious. I think that that's wrong. I think that consciousness is not something that magically emerges out of some new form of organization. I think when we talk about consciousness, all we mean is that we're interacting with the world in a certain way. And there's a whole range of ways of interacting with the world. My refrigerator interacts with the world in a fairly simple way. And I could build a machine that gradually interacts more and more in a more and more complex way. But I don't think there's any one magical point where suddenly the complexity goes beyond some phase transition limit and the refrigerator or the robot would become conscious, I think that consciousness is just a word that we use to describe things that we can do, but I think like a human baby, for example, is probably not conscious the way adults are. And as the child gets older, at 3 years old, it doesn't have a theory of mind, a theory of other people's minds like we adults have. It's conscious in a different way from us. It gradually increases its consciousness. And I think animals, whether or not they're conscious, insects, whether or not they're conscious, these are not questions of fact. They're questions of definition. Are we willing to use the word conscious when we describe certain kinds of behavior? Just like the question of whether a virus is alive or a bacterium is alive or a mouse is alive, these are questions of definition. They're not questions of fact. Okay? Do you see what I mean? I agree with you that...
Actually...
I agree with you, what you say, that probably we would not use the word conscious unless the degree of complexity were sufficiently high for us to be willing to use the word. But that doesn't mean that consciousness is something that arises in some magical fashion from this complexity. The reason we use the word conscious only for complex systems is because that's how we've defined the word. It's not because there's something magical that's really happening, starting at some special magical degree of complexity.
No, very clear. Actually, I was posing the complexity on the word side. So, because we're talking about the brain, the vat. No, so the idea was that the word has to be somehow the word outside to which I connect. The brain should be so should have the characteristics that you expect from the world. No, this was the idea. I didn't think about phase transition. I was more concerned about embodying the brain. And more or less the idea was, okay, if your computer program, a simulation program, is complicated enough or has the characteristics of the real universe, then maybe this is possible. I don't know what you think about that.
Yes, I agree entirely with what you say, but I think that there's a danger in what you say, because people will interpret it by saying, yes, well, there's something magical about embodiment, and there's something magical about complexity that is brought by embodiment that somehow generates the consciousness and generates these capacities. And I think that's not correct. I think it's just a matter of definition. That you could probably build an intelligent machine that had no body, that interacted with its world over the internet by just entirely symbolic manipulation, and it would have behavior which you might be willing to call conscious in some other sense. It would not be the same kind of consciousness that humans have, because humans have body, but I still think that these questions are more matters of definition than matters of fact. Do you see what I mean?
No, I see. Okay, thank you very much. I think we had a very interesting session today, and maybe we can conclude with the usual delay. So we have just about half an hour delay. And so thank to all the speakers, thank to all the people attending, and all the people involved in organization. And see you next time. See you. Bye-bye.